So I was helping some of your classmates a few days ago, and the problem I helped them with was interesting to me, and so I came up with an example problem of my own that I'm now going to do. And so here it is. Suppose that there's a 30 kilogram object. So mass of this object is 30 kilograms. And it was going 10 meters per second. So its initial velocity is 10 meters per second. And it came to a stop, just stopped moving within 3 seconds. And part A of my question is, and really the question, which I changed, what would be the magnitude of the net force on a 50 kilogram object? So in other words, what's the magnitude of the net force, the average net force, on a 50 kilogram object? So the way that you would solve this is, first of all, force is equal to mass times acceleration. And I'm only working with averages here. And so average acceleration is equal to the change in the velocity divided by the time. So in this case, if we go from 10 meters per second to a stop, that would mean that our final velocity is 0 meters per second. I'm not moving at all. And so change in v is v final minus v initial over time. Well, my final is 0, so 0 meters per second, minus 10 meters per second, all over 3 seconds. 0 minus 10 is just negative 10 meters per second over 3 seconds. And this really doesn't simplify any, so I would just say it's negative 10 thirds meters per second squared. If you put that in the calculator, you'll get that that's negative 3.33333. So I'll just write that as negative 3.3 bar meters per second squared. Make sure when doing calculations, if you wrote it as a decimal with the bar, meaning it's repeating over and over, to just sort of like mash the 3 key a whole bunch whenever you do a calculation with this number. Okay. Or the question might actually specify to use 2 or 3 significant places. Depends. So this is my average acceleration. It's negative because I'm going in a certain direction and the acceleration stopped me in moving in that direction. That's why it's negative. And so now I want to know what the net force is, the magnitude of the net force is. So I'm going to do the absolute value of the mass of the object, which in this case happens to be 50 kilograms, times the average acceleration, which is negative 3.3 bar meters per second squared, and I'm going to do the magnitude of that. So I'm going to plug that into my calculator. 50 times, and I'll actually use the fraction here, 50 times negative 10 thirds, and that gives me magnitude, so I'm going to ignore the negative sign here, 166.67, I rounded that because it's 0.66666 forever, kilograms, meters per second squared, which is a Newton. And so that's the average net force that a 50 kilogram object that was going 10 meters per second, which stopped in 3 seconds, that's the average net force it would experience. Now, part B, I ask, how do these compare? These being this object, the 50 kilogram object, and the 30 kilogram object. How do the net forces on those objects compare? Well, in order to answer that, first of all, I need to know what the net force was on this original object. My acceleration's the same. And so really, I would just do, let's call this Fnet 2. I need to find Fnet 1. So that's really just going to be 30 kilograms times, and I'll use the fraction here, negative 10 thirds meters per second squared. And that's going to be 100. I will still type it in for paranoia's sake, 30 times negative 10 thirds, but that's 100. And again, I'm ignoring the negative because magnitude. It's 100 newtons. So how do these compare? Well, I will grant that the way that's worded, well, there's a bunch of ways you could compare something, right? I could look at that, subtract them, and say, oh, this is about 66.67 newtons more. That's a comparison. But generally speaking, what's going to be expected is for you to do a ratio. So I'll do the ratio of Fnet 2 to Fnet 1. And when I do that, I get 166.67, well, I guess not repeating sevens because I rounded that, newtons, to 100 newtons. Notice that whenever you do a ratio, the units cancel because you're just talking about how much bigger or smaller is something. So if I now do those, I get 1.67. No units or nothing. So what does that mean? Well, if I multiplied this by 100, I would get 167%. That's just converting a decimal to a percentage. So what we would say is the force on object number 2, the one that is 50 kilograms, is experiencing 167% of the force that object 1 would experience under these conditions. Or you could say it's 67% more, right? Because 100% just means all of it. It doesn't mean any more. So it's 67% more, or 167% of the force. If you did the comparison the other way around, if you did Fnet 1 over Fnet 2, well then, of course, that's 100 newtons to 166.67 newtons, and the newtons cancel off. And if I throw that in there, I get 0.5 bunch of nines. So 0.6 really. Let's round that, 0.6, which if I multiply by 100 gives me 60%. Well, that means that object number 1, the 30 kilogram object, is experiencing 60% of the force that object 2 was experiencing. So it's experiencing 60% of the total, so less. It's not experiencing 100%, which would be all of the force. It's only experiencing 60% of the force. And so you could actually phrase that comparison either way, and it would be correct as long as you understand how to put it. 167% of the force versus 60% of the force, we would expect the heavier object to undergo more force in order to stop it in the same amount of time. That's how I would solve the problem. I made a specific point in my example of making sure that all your units were already set up correctly, kilograms, meters per second, and seconds, because I wanted to emphasize that this is actually solving the problem. Now, it could have been that you weren't given kilograms. Maybe you were given, well, this would be more rare, but for the sake of example, maybe you were given grams. Let's say that you were told that M0 is 30,000 grams. Well, I need to convert that to kilograms. So 1 gram is 1,000 kilograms. So I did that the wrong way around, but I'm going to stick with it. So in this case, you would actually have 30 million kilograms. So this thing's huge now, but the point being that if it was given to you in grams, you would need to convert it to kilograms before doing anything. But then this would still go in the same place everywhere else. Likewise, what if you were told not that your velocity was 10 meters per second, but let's say 1 kilometer per hour? Well, then you need to convert it to meters per second. So I would just say, well, 1 kilometer has 1,000 meters, and 1 hour has 3,600 seconds. Hours gone, kilometers gone. I now have meters per second, and I would just simplify that as much as possible. This would come out to be 10 over 36 meters per second, which when I throw that in the calculator, I was simplifying stuff in my head there. Don't stress about that. You'll get the same thing if you do 1,000 divided by 3,600 here. And either way, I get that it's 0.27 repeating meters per second. And then once I'd have those numbers, everything else would be the same. I would do change in v over t to get my average acceleration and then compute the forces. So sometimes you, probably a lot of times in real life, you have to do unit conversions to actually get them to line up with the units that are in the memorized formulas. But that's just unit conversion. It's not actually solving the physics problem itself. It's necessary. You have to do that before you start. You have to make sure you've got kilograms, meters per second, etc. But that's side work that you do. Once that's taken care of, then you can go through and solve the problem. And that is this example.